All right, thank you all for joining me today. Before I get to the first question, you all know each other, correct? I believe you work together on some projects centered primarily around battery technology and manufacturing. So just tell me a little bit about that. How do the three of you know each other, connect, work together? And we'll start, Jamie, do you want to go first?
For sure. Well, I know Jan Liu, or Dr. Liu, better than I know anybody else because we're collaborating on a project to take graphite that we can produce from our graphite mine in the Spokane Valley up to not just battery grade level, but to enhance it so that it basically performs even better than existing commercial formulations for electric vehicles and for other lithium-ion batteries, for that matter. So we've worked together now. Oh, it's added up to a couple of years now on that project, and this all ties in very nicely with all notions of the circular economy, and so yeah, that's how we go back, and looking forward to see how it unfolds as there's increasing emphasis on new energy economy.
Brilliant. And then that's probably a good segue. Dr. Liu, how do you work with these two?
Yeah, first of all, I get to know Jamie like 2.5 years ago when actually Jamie and also George from Eco Graphite approached us for a potential project on graphite for lithium-ion batteries. So that's how we started the conversation and eventually apply for funding and also kick off the project this year. So I'm very excited that in local BC, we are forming this university and the industry collaboration to really move towards the decarbonization economy. And for Sarah, and this is probably my first time to meet Sarah, but we do actually have a indirect relationship with tech in another project on lithium tellurium battery, because the tellurium we use actually the source is from tech, from those industry waste, and our partner, which is Phoenix Advanced Materials, they manage to recycle and upgrade those byproducts into very high purity tellurium metals. And at UBC, and we managed to turn that high purity metal into high performance lithium tellurium battery. So that's how we get linked to each other. Thank you.
Brilliant, thanks. And Sarah, it sounds like you're just sort of the orchestrator then of providing materials. And how do you connect in with sort of this mind shift?
I guess as the representative from tech and trail, like the whole Metal Tech Alley and a lot of the infrastructure that's been built around these like higher purity metals, and kind of stems from the fact that tech exists in the valley in the first place. And I know Dawn wasn't able to make it, but Dawn from Phoenix, again, tech produces like a 4-9s cadmium, 4-9s indium that gets upgraded by a local Phoenix in order to be made into like battery quality. So we provide raw materials for some of these like battery technologies, and we also play quite a role in the recycling side as well.
Brilliant. All right, well, thank you. It's good to have you all on the line. So the title of this panel is How High Tech is Refining the Metallurgical Sector. Tell me your perspective on how technology and innovation and research will enable circularity for batteries in particular, because that seems to be the commonality on this panel. But if you have a perspective on broader products also, that would be helpful. So technology and innovation research. And we might start with Dr. Liu on that one, because if it comes down to research, you're certainly the one with the most experience on this one.
Yes, thank you so much. I for sure have a lot to share regarding to how to actually enable circularity for batteries. So I want to share 3 points regarding to the recent development in battery and how that actually relates to the circular economy. So first of all, I believe everyone is aware the current vehicle battery, they are not properly recycled right now for many reasons. First of all, the current battery are not designed for recycling actually. So that's one major reason. Secondly, the current challenge in recycling technology is also limiting how we recycle the battery. So from our perspective, in order to build battery circular economy, first of all, we want to develop new materials and also new battery design so we can better recycle those materials later on. And I consider that's the recyclability of the battery materials and the battery devices. Using the example with our Phoenix Advanced Materials and also Tech, the lithium battery, and we have managed to actually use those byproducts and make them into high performance battery. In that way, we actually can diversify the type of materials we can use to power vehicle batteries. So we don't have less dependence on those critical metals, for example, cobalt. So we want to develop new materials to enable next generation battery. And the second point is regarding to the recyclability of the battery technology. On the current lithium-ion batteries, when they actually commercialized in 1991, they were not intended for recycling. And so that's why we have so challenging right now just to recover all the raw materials and then upgrade them for other use. So that's why in our current research, in addition to all the performance such as lifetime or efficiency, we actually include the recyclability in the battery architecture design. I think that's going to be a fundamental piece for future battery design, because if you want to make the recycling easier, you have to design the battery in that way. And then lastly, I think is regarding to recycling technologies. The current challenge is we have dismantled all the battery and recover all the materials. We simply don't have all the technology ready to recycle all the critical metals, for example, lithium, cobalt, or graphites. And secondly, or more importantly, the current recycling technology is hard to build a business case or sustainable business for recycling. Because even for our existing technology, recycling technology, we are able to recover some of the critical metals. But in order to really build a business case and make profits for our partners, that's quite a challenge. So that's how I envision in the following few years, developing new and sustainable recycling technology is going to be the key in order to recover, recycle all the vehicle batteries. And that's going to be a growing problem in the coming years, because the first generation of electric vehicle is going to exit the market very soon. Thank you.
Brilliant. That's super helpful. It sounds like there are quite a few points within there to expand upon and touch upon, designing with a modular structure with circularity in mind, the technology to recapture. Jamie or Sarah, do either of you want to jump in on how you view technology? Sarah, I know that you have, that's your life at this point with Race 21 and tech. So maybe I was opening it up for both, but maybe I'll throw it to Sarah then. What is your view on how technology is going to enable this?
Sure. Yeah, I guess like when you think about circularity of batteries, it varies widely depending on the battery type. And so in Tech Trail, we have we recycle lead batteries, zinc alkaline, and zinc alkaline batteries. And so lead batteries are actually highly recycled, up to 99%, and recycles back to 100% quality. So a project that we currently have on the books in Trail for 2022 is actually just taking some of these battery sludge and metallics and putting it in a different part of our circuit to just kind of like leave more room in the front end for lead feeds and bring this lead into a different part of the circuit. And so there's ongoing efforts to figure out where is the best place in our process loops to integrate recycled materials. So yeah, ongoing work in innovation within the Trail space. Zinc alkaline, we do recycle in Trail. And then to add on to what Dr. Liu said, the lithium ion battery is quite a challenge right now because we're going after very little metal compared to lead. and zinc batteries. And so where there needs to be an innovation is an effective recycling technique that actually keeps up as well with the improvements in the battery technology. An example is with the lithium ion battery. Tesla used to have 12.5 kilograms of cobalt. Now they're down to 4.5, and Elon Musk wants to completely eliminate cobalt from the battery chemistry. And again, with like Umicore used to recycle gold and silver from cell phones. But as cell phone technology advanced and thinner films could be created, the economics of recycling fell out. So to truly make circularity feasible, technology for recycling batteries has to keep up with the innovations going on in the battery industry.
That's interesting. So I know the answer, but a lot of people who are listening in on this probably don't know. Why is it important to eliminate things like cobalt and gold from products? Why is that something that companies are looking to do? Sorry?
Cost.
Cost is one of them. Yeah, that's interesting. So they're certainly expensive materials then?
Yeah.
Okay. Yeah, there's another, and I'll just interject there because it's something that I see in my work. I interact quite a bit with supply chains and traceability. So gold is one of those 3TG metals. It's a conflict mineral or conflict metal. Cobalt is also one of those materials that electronics manufacturers are very keen on because it gets sourced from the DRC, the Democratic Republic of Congo. And so there's potential for forced labor or child labor or potential human rights violations in the supply chain. So it's interesting to hear that cost is one of those levers that are being pulled, as well as potentially supply chain considerations. So that's really, that's helpful for me to hear because that gives some context to my own work. Okay, back to technology, the whole point of this conversation. Jamie, please let us know how you see technology revolutionizing the recapture of products, how this fits in with the work that you're doing.
From the perspective of just looking at graphite in isolation, there is an awful lot of work that has to be done to improve any recoverability of the graphite from a lithium-ion battery. Part of the reason for that is that unlike the metals in the battery, we've currently worked out no way to reuse the graphite inside a battery. So that graphite for now, we have to work out new ways to use all of this graphite that's going to come out of the battery. And to put it in perspective, there's at least as much graphite in the lithium-ion battery as there is any other mineral. So the graphite is basically one slice of bread in a sandwich in the lithium-ion battery, and it actually occupies quite a bit of space. The world has yet to face a huge shortage of graphite, so we don't really hear a lot about the graphite in the news of lithium-ion batteries. That may well change if we get a shortage, but for the time being, it's somewhat overlooked. And the risk that we run is that after the upcoming ramp-up period of creating all kinds of different or huge volumes of batteries, mainly for electric vehicles, we run the risk that when it comes time to recycle all these things, we may well be in a position to recover most of the metals, especially the highly valuable ones. But then we could be left with all kinds of black powder that isn't useful anymore for the batteries. And if we haven't by then figured out how to redeploy that material, we've got some messy stuff on our hands. So this is one area where technology has to improve. The other possibility, I suppose, is that somehow we work out how to recover the graphite in a form that it is usable. But it's technically a very hard problem. So I'm not especially optimistic about it. But this is going to be one of the challenges that we're going to be facing in the next, call it 5 years, as volumes of returned battery material start to become available, and there's a call for recycling the materials and not creating huge waste dumps of this stuff. Jillian, you're
I am muted. I was like, and I'm muted. Yeah. This is the world we live in these days. Brilliant. So it sounds like there are quite a few different options in sort of that circular model, that spiral of bending waste back in. where technological advances could be enacted. But it also sounds like there's this larger ecosystem of participants that are required. It's many steps along the way. There are suppliers, there are recyclers, there are manufacturers. So is this feasible on a global scale? Or is this something that has to happen in microcosms? What are the alternatives? And do you know of any examples that are happening on various scales? And I haven't started with you yet, Sarah. So if you'll forgive me for calling on you first for this one, what's your vision of how this might work at a large scale, small scale?
Yeah, so again, to use lead as an example, so lead battery recycling is a pretty good example of recycling on a North American scale. So we sell the refined lead to the battery producers, they sell to the manufacturer, they sell to the consumers, eventually the collectors, the batteries are collected, sent to crushers, sent to recycling facilities, and then comes back to us. And so that's an example of where it is feasible and where all of the steps, all of the people and steps in the process are in place. With alkaline batteries and lithium ion, we have some work to do to get that ecosystem in place. The question of whether it's feasible on a global scale. So currently there are some challenges moving batteries across borders because they're defined as hazardous waste. So that's currently something that creates some barriers for globalizing the process, I suppose. And an example of micro scale, I guess, is like this small ecosystem we have in the trail area where we provide these 4,9s indium and cadmium to Phoenix, where they, as an intermediate product that they further refine for use in batteries. And then we also work closely with the local battery recyclers, KC Recycling and Retrieve, where we're the consumer of recycled materials. So at KC, they break lead acid batteries and send us the acid separators, metallics, and sludge. We also get the zinc alkaline batteries, and we also recycle CRT glass from KC. They break the electronics there, and we recover parts of that. So there are some examples where in a smaller scale, there's some recycling that can happen.
Brilliant. Yeah. So for real, I will throw it up to either Dr. Liu or Jamie this time. What's your vision? How do you see this working? Is it something where we'll be able to have a global circular scale of shipping and going various places with all the various parts that need to happen? Or is this something that has to happen at a smaller scale?
I'll jump in here. Again, speaking from just the narrow point of view of the graphite component of things, graphite, I would love it if graphite were 10 times as valuable as it is, and it would be up there with some of the metals involved in batteries, where there's a clear incentive to go extract that material and then put it back into the economy, whether it's back into batteries or something else. But fact of the matter is, the material itself, especially as a recovered product, is not going to be valuable enough to be sending all over the world in a supply chain where or a recovery chain where you're shipping stuff overseas every time you want to extract one mineral from it. So I foresee this working. The only way that I really foresee this working is if there are recovery centers that are capable of extracting all of the materials of interest all in one place, rather than breaking something apart and then having to send the graphite components and the graphite heavy components off to some place. Bagging stuff up, shipping it off to a new center, and extracting it's just not going to work because it's just going to cost too much. So I think there are going to have to be centers where everything is handled all at once. So I think it's going to take quite a bit of cooperation, and basically a recovery center is going to have to be a hub for marketing all of the recovery, closely twinned with those recovery centers.
Yeah, Dr. Liu, what's your perspective on that?
Yeah, thank you so much. I totally agree with Jamie about, I think one of the main challenges for building a global ecosystem is actually the logistics challenge. Because we already have some examples locally that the challenge actually is not on the technology side is actually is how to make the recycling process sustainable. I do, for example, Sarah actually just share one example about the lead acid battery in Trio. I think it's a great example how to actually make the recycling sustainable. We really have to figure out, how to actually collect them and how to send them to recycling center, and recycling center make those recycling materials profitable. Another example actually is happening at the UBCO. Actually, is we are working with another partner to recycle carbon black from retired tires. So all those mining tires. On the recycling side actually is pretty successful, but one of the challenges is for how to actually shape those retired tires, to the recycling center, then send out all the carbon black for different applications. So that's one practical challenge other than recycling and recycling technology. But I do see this potential actually in previously we do have actually quite a few very good examples, how to build the circular ecosystem at a micro scale. And the global scale, I pretty much agree with Jamie. The challenge actually is, how you have to shape things around the world. That's pretty challenging right now. Yeah.
Yeah, that's in carbon reporting, that's what we would call scope 3. You end up putting emissions on the transportation side of things to move everything from one place to another. And that ends up, are you really adding environmental value to doing that? So it sounds like what I'm hearing is that instead of having many places around the world where you have specialized recycling, it might make a little more sense to have generalist operations at a local scale so that you don't have to have that collection and shipping and all the infrastructure related to that. But of course, then that presents additional challenges of how do you get that recycling technology distributed throughout the world. Am I summarizing that correctly? Yeah, okay.
In some ways, I see it like it's almost similar to bottling plants. I mean, Coca-Cola and Pepsi, they're all over the world. They're giant corporations, but they have production and distribution centers all over the place. They operate at the micro scale. It's just that they do it thousands of times over in the world. So perhaps we need something that's akin to that model.
I'm glad I'm not the only person that thinks in analogies. I think that's a great way of looking at it. Yeah, that we just need to make this so commonplace and so easily accessible and sort of mind share through everything. I don't know how possible that is, but yeah, before I go off on any tangents here, let's stick to the questions and then we can expand on that before we get to the Q&A part of this. So one of the points, Dr. Liu, that you touched on is that we need to ensure recovery at the end, and that's partially a technological solution that we need to implement to overcome, make sure that we can recover everything, but it's also a design function. And historically that hasn't been designed into products. Circularity and recovery hasn't been in mind. So how do we ensure that? What are some of the options in both of those areas that we can dig into and discuss on this panel? I'm opening that to everyone.
So maybe I go first for this round. So for the designing circularity for let's say for battery or any other technology, I think that first we have to realize that this is very important and is possible. So that's the first thing for the product design. And right now for the battery part, especially the solid state battery we are working right now, because this type of battery is significantly different from conventional liquid-based lithium-ion batteries. Now we got the opportunity actually to redesign the structure of the battery, so it's going to make the dismantling and recycling easier later on. So that's one thing I think we really have to build into the battery design in the very first place, even we demonstrate the battery and before we even manufacture the battery. And the second thing for the designing of circularity is before we even develop the product, we really have to think about at the end of the life for the product, how do we recycle them and who is going to recycle. And I think it's better if we can start, that conversation and also streamline from design, manufacturing, and recycling. So that's going to help to enable this circular economy.
Sarah, Jamie,
Yes, sure. Yeah, so I guess, the key aspects to this is you must recover the batteries when they reach their end of life and have the infrastructure set up to do so, like we do in lead recycling. But then there's also this piece of, on the recovery piece, ensuring that you get maximum recovery within your processing steps. And so this is currently an interesting space as tech is moving towards this digital transformation called Race 21 and has made a significant investment in better leveraging data to improve recoveries and other business drivers. So examples of the type of work being done to improve, for example, lead recovery in the chipset, which partially comes from recycled lead, are things like advanced process control for residue blending, complex instrumentation that is being installed to withstand high heat, high dust, high accretion, and will hopefully enable us to apply machine learning models to support fueling decisions. This Race 21 program that Tech's undergone is also looking at recovery in the mining operations. So where we do have to bring in primary ore, still making sure we're recovering effectively. And so technologies that look at tracking ore characteristics from the dig phase all the way through the process in real time and applying advanced analytics. So in the space of recovery, in spite of these technological improvements, recoveries will never be 100% in our processing steps. Even if you have a good recycling chain, there's still likely a place for primary to account for losses and growth of the market. And on the concept of designing for circularity, when you're designing, you should have recycling in mind, whether it's metallurgical, material, or physical characteristics of the batteries. So examples of different challenges we've encountered with recycling and trail are with the zinc alkaline batteries. When we first started treating them, they had high mercury, which caused mercury to build up in our circulation system and caused us to only accept North American batteries. So that's an example where we start rejecting certain products based on like metallurgical capabilities. We've had challenges with posts with the lead batteries. They can't be ground, and so we're unable to feed them into our process. And in our local recycling facility, we've seen a challenge where batteries aren't traditional anymore. They've gone more to this absorbent glass battery technology, which is very difficult to process. And our current recycling facility actually cannot handle it. It's plugging screens. And right now they're dealing with it by increasing manpower to pressure wash the screens every 10 minutes. But if we continue to not be able to handle it, it's a $4 million investment to upgrade our screen technology. So when the design changes are made, if they don't consider the recycling facilities, it creates challenges for these recycling facilities, and either the material gets rejected for recycling, or the cost to modify the process is getting passed on to the recyclers to make the investment. So designing for circularity requires the manufacturer to design the product in a way that's easy to recycle.
Gotcha. Thank you for that. Yeah, and Jamie, I think when we first started talking about this this concept in some of our pre-calls, you mentioned that it's not just a technology issue, it's also a human issue. You have to impact human behavior to be able to then recapture that. So I'd love to hear your perspective on what technologies could help with this, but also maybe what other approaches we're going to need to make sure that people are willing to do their part and participate in this.
Sure. I think there have been some technologies come along recently that could really help a lot in terms of enabling efficient tracing of recovery of materials, and basically means to encourage building in recovery into the original design of the batteries and the inputs to the batteries. Ultimately, I think it has to revolve around incentives to do this. anybody's going to, or the reason that anybody's going to bother having a traceable supply chain and putting tags or whatever is needed on batteries as they go through the system, and then scanning those tags when you recover it, and then recover the material, and then say, okay, well, producer of lithium product X has successfully seen their material go through the life of the battery, and now it's been recovered again, so now they deserve some credit for all of this. There has to be some incentive to do all this, or nobody's going to bother. Just as with recycling of drink cans or something like that, and until there's a deposit on the drink cans, they're all going to go into the local dump. Once you start putting a little bit of incentive, and it's amazing how little that incentive has to be. Once you have a little bit of incentive for people to all get together and start putting their materials back into the production stream again, now things start almost it's almost like the invisible hand taking care of it itself. Of course, it's not invisible because it was the deposit behind it. But that sort of thinking has to become commonplace, and it has to be. Unfortunately, I think it's going to have to be mandated that these things are included. So it has to become a competitive disadvantage not to have your materials designed for recyclability and to not see them through to the point where recovery actually happens. Right? This is the way that we ensure that we don't have stacks of stuff because people can't be bothered to do the right thing with the leftovers from what they produce.
Yeah. And again, I'm so glad you think in analogies. I'm
not sure I would think if it weren't for analogies.
Yeah, well, we are saying that on camera, but hey. Yeah, it's certainly, I feel like putting a deposit on that material also signals that the material that's in this has value that we want to retain. And that's the entire premise of the circular economy, is these materials have value. We want to make sure that the value that graphite has, that the lead has, that the lithium has, ends up staying, and we're not just literally throwing that out. So I think that also sends the right signal to people and the market and companies everywhere.
Sometimes we don't even realize what that value is until an effort is put into actually figuring that out. Right?
Oh, for sure.
Inertia is a powerful thing. So if you change it up and start actually getting people doing stuff, sometimes we discover that, oh my goodness, there's a real wellspring of material here that has serious value that we never even realized would be the case.
Yeah, and everyone on this call, myself excluded, is working really hard to be able to clear the path so that once that value is understood and realized, everything is in place so that can then be recaptured and reused. So I guess the next question I have is, clearing the pathway for that material and reusing it. Do we have enough materials in that potential waste feedstock to ensure a pure circular economy? Or are there potential limitations in place that would make that unreasonable, unfeasible? And what's the role of raw materials then? And maybe, I don't know, I could call on any one of you because there's connections to smelting, to product design and research, to raw materials provision itself. So anyone who really feels passionate about this, please speak up. Or be polite.
Well, in the case of graphite, again, I'm prefacing everything as in the case of graphite, there is so much more graphite going to be required for electric vehicles in the next, say, 10 years. And perhaps even beyond that point. There's simply not enough in circulation now to support the growth of electric vehicles that we all want and expect. So there's going to have to be a huge ramp up in graphite outputs over the next little while. However, that doesn't really relieve us of the responsibility to figure out what to do with this graphite when the bill comes due, as it were. These batteries are not going to last forever, and there is good incentive to recycle a lot of the components of it, and we simply don't want to have massive piles of spent graphite lying around when it should be used for something useful. It will certainly be a useful material for something, but we have to do the work to determine what that's going to be and to build the markets around that availability.
Yeah, as I mentioned on the last question, like recoveries will always be a challenge, and the only place where you can get a pure circular economy is if you have declining use of the product. In line with what Jamie was just saying, even though lead is 99% recycled, the lead demand is going up by 3% a year. So including losses, you know, there's still a demand for primary. And metal is probably one of the places where you're going to get closest to that ideal because you can recycle them back to their original quality. Yeah, so, and I guess just in line with that, I'm in line with the last kind of comment, the theme around we have to change the perception and change the consumer behavior. Is just like even an example in lead is that we currently in Trail get a premium for our lead product because it's a primary lead product and doesn't come from primarily recycled lead. So until there's like a change in the way people perceive recycled products and the quality of recycled products, yeah, it'll be challenging to get them to pay more for recycled materials.
Yeah, for the amount of materials to enable the circular economy, I mean, as human being, we always ask for more. So we don't have unlimited resource. So that's a reality. You know, for basically for anything, it's going to be okay for a period of time, but after a certain point, it's going to be a pressing issue. And for example, for graphite, we do have a large amount of graphite that's available for electric vehicle. But in the downstream, if we move on to recycle the graphite from battery, even though those graphite we cannot put back to battery, but they are certainly valuable for other application. For example, we can also upgrade those recycled graphite into graphene, right? Which has very broad application right now. But even for those applications right now, the industry, they tend to go for the raw graphites, you know, and which they actually pay a lot more. So we have to really explore more application for those recycled materials. And regarding to the role of raw materials in this circular economy, I feel like raw materials is critically important in order actually to basically start everything. And in particular in Canada, I think that's one of our strengths in the raw material. If we look at the raw material supply in Canada, basically we have everything we need. For example, lithium, graphites, and also cobalt. But we do have to also build other infrastructure, for example, battery manufacturing locally, so we actually can combine our strengths in the raw material supply chain to really maximize our outputs. Yes, thank you so much.
Yeah. So it sounds like, I mean, all three of you are tackling this from different aspects, whether it be product research and design, or raw material sourcing, or the recycling process and optimizing that. So I think there's quite a bit here to unpack. I know that we're bumping up a little bit on time, and I want to leave time for Q&A at the end. But is there anything from your particular perspective that you want to leave the structured portion of this panel with before we hop into the Q&A? So floor is open for anyone to give their perspective on this topic. If not, I have a perspective.
Go ahead.
Excellent. Yeah, I find it fascinating because so my background is very much in chemistry and environmental science. So I come at this from a very different perspective than all of you. But I find it absolutely fascinating how companies are really starting to think about this and enact it. It's not just theory anymore. It's action. So we have Race 21, of course, enacting some process optimization and big data analytics to then streamline and optimize the recycling process and the metal production process. And I see other tech organizations integrating it into design, whether it be life cycle assessments or designing for circularity. There's one, when I was doing research for my keynote that I have at this conference also, I came across a cell phone company that is designing for circularity out of the Netherlands. So it's modular. So if you want a better camera, there's a better camera module that comes out. You can then just swap it out. And it's designed for circularity. So all of the module parts of the cell phone are more easily recaptured. And of course, the marketing makes that really cool and sleek. And so there's a bit of a premium on that one. So I find it really interesting that this isn't just theory anymore. It's something that people are really doing. And of course, all three of you are evidence of that this is something that's being put into practice in industry and in collaboration between research and academia and industry. So if there are no other comments, I'll pause for a moment just in case there are. Okay.
I will say you're right. There's a newfound emphasis on called ESG factors in corporate behavior. You know? One of the risks that companies face right now is if they're caught or even perceived to be behaving irresponsibly. So this is a new emphasis of corporate responsibility for all of the stakeholders involved, and not just the narrow interests of the shareholders.
For sure. Yeah, and if you get me on that tangent, I don't think we'll ever get to Q&A. So. But thank you all. Thank all three of you for your time. And at this point, we'll open up for live questions from the audience. So thank you so much.